Launched in 1977, NASA's Voyager 1 spacecraft has become the most distant human-made object ever built, traveling farther from Earth than any other machine in history and crossing into the uncharted realm of interstellar space. What began as a modest 4-year mission to explore Jupiter and Saturn has transformed into an extraordinary decades-long journey that continues to astonish scientists and inspire the public. Built in an era when cassette players were cutting-edge technology, this bold spacecraft still sends back valuable data for more than 14 billion kilometers away. A feat of engineering and perseverance that almost defies belief. Voyager 1 continues to communicate with Earth using just 23 watts of power, less than that used by a common light bulb. And with only 69 kilobytes of onboard memory, that it continues to function at all is nothing short of miraculous. These aging yet remarkably resilient machines are not drifting aimlessly through the void. They are still actively performing science, collecting information that challenges our understanding of the universe. The entire venture traces back to a visionary insight by Gary Flandreau, a scientist at NASA's Jet Propulsion Laboratory, who used nothing more than a pencil, paper, and his analytical skill to recognize a once-in-176 years opportunity. In the late 1970s and early 1980s, the 4 outer gas giants, Jupiter, Saturn, Uranus, and Neptune, would align in such a way that a spacecraft could use each planet's gravity to slingshot to the next in a precise cosmic choreography. This planetary alignment formed a kind of celestial necklace, creating a route that would cut the travel time to Neptune from 30 years to just 12. Knowing that this chance would not come again for more than a century, NASA acted quickly, launching 2 nearly identical probes, Voyager 1 and Voyager 2, just 15 days apart during the summer of 1977. What followed was a mission that would shatter all expectations and become one of the most profound achievements in the history of space exploration. The Voyager's original task was to conduct a close-up survey of the outer planets, and the results were groundbreaking. Voyager 1 flew past Jupiter and Saturn, revealing the swirling chaos of their atmospheres and the complex dynamic nature of their moons. Among its most remarkable findings was the detection of active volcanoes on Jupiter's moon Io, the first time volcanic activity had been observed beyond Earth, and the discovery that Saturn's moon Titan possessed an atmosphere even thicker than Earth's. Meanwhile, Voyager 2, on a different trajectory, became the only spacecraft to visit Uranus in 1986 and Neptune in 1989. These encounters unveiled magnetic fields, unexpected weather patterns, and ring systems around planets previously thought to lack them. Far from being cold, dead worlds, the planets of the outer solar system turned out to be dynamic and surprising. By the late 1980s, the Voyager's planetary missions had been completed, but their journeys were far from over. Their next destination was not a planet, but the great unknown beyond the Sun's protective bubble, the interstellar medium. As they moved farther from the Sun, they continued to study the solar wind, cosmic rays, and magnetic fields, sending their data home through NASA's Deep Space Network. Communication relied on giant 12-m-wide satellite dishes. And while radio signals still traveled to the speed of light, the immense distance meant each message faced a round-trip delay of more than 20 hours. The data itself was stored on old-fashioned 8-track tape recorders before being beamed back to Earth. In size, the spacecraft were no larger than a Volkswagen Beetle, and they operated autonomously using primitive software and backup systems created in an era long before smartphones or high-speed internet. Their journey to Jupiter alone required traveling 10 times the distance from Earth to Mercury and navigating through the asteroid belt, a region once feared impassable. Their safe passage helped confirm that spacecraft could travel through the belt without catastrophic collisions. Along the way, both Voyagers contributed to our understanding of the heliosphere, the vast bubble of space dominated by the Sun's magnetic field and solar wind. The edge of this bubble, called the heliopause, marks the beginning of interstellar space and became the ultimate target of the extended mission. Scientists closely monitored the data in hopes of catching the exact moment the probes would cross this invisible frontier. Voyager 1 reached the heliopause on August 25, 2012 at a distance of about 121 astronomical units from Earth. 1 astronomical unit being the distance from Earth to the Sun. The crossing was not as simple as expected. Rather than a sudden change in magnetic field direction, Voyager 1 detected a dramatic increase in plasma density, a sign it had entered a region no longer dominated by the solar wind. Curiously, the magnetic field direction remained largely the same, leading to initial confusion. It became clear that the boundary was not sharp, but instead a turbulent diffuse frontier where the solar and interstellar environments mingle. Voyager 2, traveling more slowly on a different path, crossed the heliopause on November 5, 2018, confirming the increase in plasma density and validating Voyager 1's earlier observations. Together, these crossings marked humanity's first physical entry into the interstellar medium and offered data that had never before been accessible, deepening our understanding of how our solar system interacts with the galaxy. Beyond the heliopause lies the hypothetical Lord Cloud, a vast shell of icy bodies thought to contain the building blocks of comets. It will take thousands of years for either Voyager to reach even the inner edge of this region, but their trajectories carry them ever outward toward the stars. The continued operation of both spacecraft is a testament to human ingenuity and scientific ambition. Every day they communicate from distances no human will likely travel in our lifetimes, returning data that informs our understanding of space physics, magnetism, and cosmic plasma. Keeping them alive requires careful management of dwindling power reserves and aging systems. Engineers have shut down non-essential instruments to conserve energy, aiming to keep at least some sensors operational into the early 2030s. Each choice is difficult. Deciding which scientific instrument to sacrifice next in order to prolong the mission is a constant challenge.